Magnetic spectrum. There are 7 different categories: radio, microwave, infrared, visible light, ultraviolet, X-rays, and gamma rays. You can pause the video if you need to copy those. Okay, so an electro, you're going to be taking notes on that list. So move to a different place in your notes, take this down. Okay, describe how an electromagnetic wave looks. So here's the idea. You have an electric field, the blue, and a magnetic field, the red. Okay? You don't draw this, just watch. Okay. So, foundational fact number 3 when we were studying electromagnetism was if a conductor experiences a changing magnetic field, then voltage is induced. That's how generators worked. Okay? If you dig a little deeper, more foundational, what you'll discover is if a magnetic field is changing, it actually creates a changing electric field. Okay? So if a magnetic field is changing, it creates a changing electric field. If you dig a little deeper, you find the reverse is true. A changing electric field creates a changing magnetic field. But doesn't a changing magnetic field create a changing electric field? Yep. But doesn't a changing electric field make a changing magnetic field? Yep, that does too. So, so you're saying they cause each other? Yep, they do. And we're really glad they do. So what happens is you have an electric field that's changing. It's a wave, which creates a changing magnetic field, which creates a changing electric field. And this electromagnetic wave propagates, travels through anything, including space. It doesn't need a medium. It creates itself. Okay? And it does the E&M. So on the problem floor, like, boom. They ever like get a circle around you, you can like break this out. Like, you'll be that cool. Okay? So, okay. All right. So an electric field and magnetic field oscillate perpendicular to each other. Okay. Is it possible for electromagnetic waves to travel through space through nothing? Yes. They are self-perpetuating, self-sustaining. We'll say self-sustaining. I don't know how to spell that. Self-sustaining. Okay. They do not need a medium. Take that wherever. Okay. And it is a really good thing they are, because in order to get light from the sun, or any energy from that matter from the sun, it has to go through space, through nothing. But yet it gets here. Okay, good with that. Okay. So, what is the speed at which electromagnetic waves travel through a vacuum, through space? The speed of light. The speed of light is special. So just like the acceleration of gravity has its own variable, g 9.8, this is lowercase c, 3 times 10 to the 8th meters per second, the speed of light in a vacuum. Okay. So the equation for the speed of a wave, this is our first equation that we learned in this unit, was speed of a wave is equal to frequency times wavelength. This is a general equation. So for the electromagnetic wave, what speed can we use? So representing speed is 3 times 10 to the 8th. So this is specific for E&M waves. I will not give you this equation. I will give you this equation. I will give you this. You need to recognize, oh, hey, that's an electromagnetic wave that's traveling at the speed of light, so I need to put C in for, or 3 times 10 to the 8th meters a second in for my speed. Good with that? So, if they all travel the same speed, how could you make a difference between different electromagnetic waves? What changes? Tell your neighbor. What could possibly change if the speed of all electromagnetic waves are 3 times 10 to the 8th meters a second? So you could do what? Change frequency or wavelength. How is frequency and wavelength related? Inversely related, because the left side is fixed. As one goes up, the other one has to go down. Good with that? Okay. That is pretty much the extent of the math of this last lesson. Okay. Good with that? So here we have a chart of the electromagnetic spectrum. Radio, microwave, infrared, visible light, ultraviolet, X-rays, and gamma rays. Okay? And as you can see, the wavelength is bigger this way, frequent, and shorter that way. So the trend is wavelength is shorter this way and longer this way. Therefore, frequency is, wait a minute. Sorry. is a longer wavelength, shorter wavelength going that way. Therefore, you have a lower frequency and higher frequency going this way. I would put that on your chart, like those where you wrote your 7 categories, kind of like show the trend of wavelength and frequency. Does that make sense? So like you wrote radio, then microwave, or ultra infrared. I would say I would do this, like wavelength, frequency. Does that make sense? Okay. All right. So our wavelength, the spectrum of that goes from hundreds of meters down to the diameter of the nuclei of an atom. That is a vast array of different wavelengths and corresponding frequencies. Cool with that? Okay. I have one more piece of information to put right here, but the rest of the time you're just kind of like listening, paying attention, and appreciating the world around you. Okay. Do that. So, first up are radio waves. Okay. So, obviously, radio is in that realm, in that category. So, AM, FM, XM. Like when you're in the radio, when you tune to a station, it's like 93 point whatever. That's the frequency in megahertz. On an AM station, I think that's kilohertz. Okay, so the whatever the station is, they're saying their frequency. So you're tuning into a certain frequency. Okay, so if you're getting TV not through cable or the internet, you're getting it via radio waves. Anything that we need to connect to satellites, we're using radio waves to get there. Radio waves have long wavelengths and can travel long distances. So radio waves, this is what we're using to talk to stuff long distances away. There's that. Okay. Microwaves. This category is huge in terms of what impacts our lives. My guess is when your kids take physics, we will have subcategorized this because microwave category, because there'll be so many different applications. So first off, let's talk about something that we've heard of all in use, our microwave ovens. Okay, so there's a certain frequency that water molecules resonate at, vibrate at, they like dance to. Okay, that frequency happens to be in the microwave category. Okay, that's why when you use a microwave oven, things that have water, have some kind of water content in them, cook better than things that are drier. I don't know if you've noticed that, but that's a thing. Like oh, this is kind of like, add some water. Just a little bit, it'll do wonders for your microwave cooking abilities. Do that. Okay. Cell phones. How our cell phones talk to the towers. Those are microwaves. Okay, it's sending information through microwaves. Now, some people freak out because like, oh, microwaves. That's like right by my head. I'm gonna like nuke my head. Like it's like sticking my head in a microwave oven. That makes sense? Like it's a microwave. It's a microwave. It's a microwave. Like why? ah, but in order to resonate something, it has to be at that specific frequency. We stay way away from that specific frequency that vibrates water molecules with cell phones. There we are with that. So you're good with cell phone usage. Okay, it's not going to zap your brain. Okay, Wi-Fi, Bluetooth, all these are microwaves in the microwave category. Okay, when we were talking about microphones with sound, some people ask, well, what about wireless microphones or any type of Bluetooth, whatever devices? Okay, here's how information is sent. So there's a transmitter that sends out, that creates electromagnetic waves doing this thing. Okay, and those waves hit the antenna. Antenna is just a stick of metal that has a bunch of electrons, and when that electric field hits those electrons, it makes them move up and down, which is exactly what an alternating current is. So information can be sent from your phone to your earbuds via electromagnetic waves through space. Oh, come on, kids. That was like in your life applicable.
Why don't they use like radio waves for Wi-Fi or Bluetooth?
Great question. So the longer the wavelength, the farther it can travel, but the less information it can carry. So you can pack more information on higher frequencies than you can lower ones. And in the past, we used radio waves a lot. And so microwaves are kind of like this not unexplored, but unclaimed territory on the electromagnetic spectrum. Okay. So, if our eyes could see microwaves, it would be like blinding. Like, wow, they'd be all over the place, coming from your phone, coming from the hubs, like going, I want to send a page to the printer, like it's just all over the place. Good with that? Okay. Next up, infrared waves. So this is commonly associated with heat. Anything that is above absolute zero emits infrared waves. Okay, so you can have cameras that are sensitive to infrared. They're called heat imaging cameras. Okay, you can pick up stuff sort of like if you've ever seen the movie Predator, like that's how Predator sees. Okay, you can use these cameras in a lot of different applications. Like you can take an inventory of your house to see where heat is leaking out. You can figure out if there's a short in some wires, or if pipes are clogged by putting hot water down the pipes, see if they turn hot, or a lot of cool stuff. Okay. So another application of infrared. See this light bulb? Okay. You see it turning on and off? Oh shoot, you can. You shouldn't be able to see that. No, you can't see that because our eyes aren't sensitive to infrared. But cameras on our phones are. You see that? Everybody good with that? Let me know if I take my. Okay. And so I can take, this is shooting infrared rays that you can't see, but it is sensitive to that. That's. So why can we see it on the phone and not like? So our camera is sensitive to that. It reads that. It registers that, but we can't see that. But since it's going through the camera, that's how we can see it. But it's going through the phone because our phone associates that, gives it a color. Okay, that picks it up. Okay. Yep. Good question.
So is the color of light we see on our camera phones, is that kind of associated with the wavelength of the infrared wave?
Yeah, I don't know. Like it's miscolored. Like I would put it more of like a red color because it's infrared, but it looks purple. But that's just how it registers in the code. Cool with that?
So then does like night vision or something like that work similar to this?
Great question. No, night vision just takes the smaller amounts of light and magnifies it. So it's looking at visible light. When we take flash photos like on our phone, you know sometimes the eyes like the red color. Is that like the same situation? It is not, but great question. That is a reflection of the back of your retina. Oh. It's like the retina in the back of your eyeballs acting like a mirror, and it's reflecting that. So that's why you can see like cat's eyes, raccoon's eyes, dog's eyes in the dark. They're looking right. They're like, "What's that light?" And they're looking right at it, and it's like it's reflecting that light off of the back of their eyes. So next up is visible light. This is the part of the color spectrum that we see. This is the Roy G. Biv. I don't know if you ever heard of that acronym. Red, orange, yellow, green, blue, indigo, violet. Personally, I'm more of a Crayola kind of guy. Kind of like the red, orange, yellow, green, blue, purple. Roy G. Like, doesn't have quite the ring to it, but I'm like, indigo? Really? Like, I know they're looking for a vowel in the, I don't know. Okay. Now, here's something I want you to appreciate here. Look how small of a section this is that we can see compared to the whole gamut of electromagnetic waves. Okay. Just a itty bitty bit. Okay. All right. Next up, ultraviolet rays. Usually, we associate this with sunburns and skin cancer. Okay. This comes from the sun, and so some bugs actually can see into the infrared spectrum. Okay. This is ultraviolet spectrum. So this is just beyond the purple side. Ultraviolet. So UV rays coming from the sun, some penetrate. These are fine. Some don't penetrate the ozone layer. These are not fine. This is what gives us cancer. Okay. So check this out. You see that in the background here, this like wavy line and then that. Okay. Those are the electromagnetic waves, the frequencies that get blocked by our atmosphere. Okay. So if we were looking at energy carried by the wave, the higher the frequency, the higher the amount of energy is carried. So this is the last thing that I wanted you to. Yep. Okay. So if we're looking at what gets blocked and what doesn't, So some radio waves, like the really, really long ones, get blocked, but a lot of them don't. And so when we are looking for life on other planets, we are using radio waves because that goes through our atmosphere. And like if you see these big satellite dishes, they're tuned for radio. Um, Here, microwaves, a lot of microwaves don't get in. That's really good because one of those is specific for resonating water molecules. Like bad news bears, okay? Some infrared gets through, but some doesn't. This is good because we get heat from the sun, okay? Visible light gets through. That's really nice. We can see the sun. We can see the stars at night. I mean, that's a pretty cool feature. From here on, gets blocked. But because from the energy is higher from here on, all this stuff, guess what? Would give us cancer. All this. Wow. Our atmosphere. That is a pretty nice feature. You know, we should probably do something to like take care of that. Just thinking. Nah, I'll let my great grandkids have 5 years and whatever. Nope, they'll just die. Okay. So is that good? Making sense? Just here's just another soapbox. Um, these guys, you like them, yeah, you like them now, but when you're 80, you're gonna be like kicking yourself. Doesn't matter, I'm gonna die anyway. You're like, okay, well, you might tell your future self that, like, you're fine, you're gonna die anyway. Like, I don't think you'll appreciate that 60 years from now.
Wait, so how are we able to see the sun's color, and like how is it also able to produce the ultraviolet rays? Like how does it produce both of them?
So it produces all types.
Okay.
What gets through our atmosphere is are these frequencies, the stuff that like some of those get through. Does that make sense? But these are blocked. It's producing all of that. I'll show you a picture here in a second of that. Okay. All right. Next up is X-rays. So X-rays have high enough energy to go through soft tissue, but not like skin, organs, and stuff like that, but not bones. So this makes it great for photographing bones. Here's how this works. It gives you cancer if you get enough of it. So that's why they put a lead smock on you to protect you from that. Okay. So here's actually a photograph, an X-ray photograph. So they have some source of X-rays that shoot X-rays through your hand. Okay. And then they have a camera, a receiver that absorb it. The ones that get through, they're light. The ones that don't get through are dark. This is actually a photograph using X-rays. And then to evaluate it from a photographic point of view, we take the negative image of that. We flip the color. So what we will look at is this. So we can see breaks and different characteristics, cavities and stuff. Does that make sense? Okay, so this is actually an X-ray photograph. And then we take the inverse of that to evaluate it. Good? Last up, gamma rays. Okay, so this is the most energetic. Some of which, so you did this in chemistry, so I've been told alpha, beta, gamma. Okay, some of those gamma rays are actually so energetic they can go through lead. Okay, we usually associate gamma rays with like nuclear radiation, like electromagnetic radiation. Technically, from a science point of view, all these electromagnetic waves are radiation, but this is what we associate with death and radioactive material, like that type of stuff. atomic bombs create gamma rays, radioactive stuff. So,
gamma rays, are those the reason Chernobyl was out?
Yep.
Yeah, that's gamma rays.
Yep.
How do MRIs work then?
Those are, they're not gamma rays. Those are magnetic resonance imaging. So it actually causes your molecules to resonate in some way, but it's not this at all. So they use magnetic fields to somehow make your tissue dance a little bit. I've read about it before. I can't remember exactly how it works, but it's not gamma rays. It's magnetic fields.
Wait, so if gamma rays can go through lead, how does our atmosphere stop?
Good question. I know. Best guess. I don't have a definitive answer. I'm just like, you ask the question, so I'm using what I know to try to figure it out. So lead is super dense, and so it's just trying to get through the atoms themselves, just like ducking, dodging. Okay. Atmosphere, like the stuff in our atmosphere, resonates with certain particles, so it isn't like it's trying to dodge it. It just happens to resonate with it and scatters it off, rather than just like, this is just like brute force trying to get through. Our ozone layer atmosphere has certain particles that, like, it's like a force shield. That's a bad explanation. It resonates, so like it's impenetrable to that. I don't know about impenetrable, but it definitely blocks a lot of them. Not because of the thickness, but because of the characteristic of our atmosphere in relation to the waves. Best guess. I'd have to look that up. You could look that up. All right. So, cameras have been developed to be receptive to different types of electromagnetic waves. And we've taken pictures of that with the sun. Okay. Now, these pictures, they associated color with them. They assigned color to them. Okay. So the colors are made up. Okay. So radio, this is what the sun emits: radio waves, microwaves, infrared, visible light. Why they didn't make that yellow, I don't know. Ultraviolet, X-rays. They should have made that purple at least. I don't know. And then gamma rays. That's what, if you could see gamma rays, that's what it looks like. Good?
Yeah. I have to print off the spreadsheet. Can I do that when I come back to it?
Okay. And then here's pictures of someone holding a cell phone with different type of waves. Good at that? All right. Give that one a shot. When were you taking the lab quiz? When were you taking the lab quiz?
10,000.
Okay, that's right. Correct answer is E. They all travel the speed of light. Good at that. Which one has the highest frequency? Correct answer is gamma rays have the highest frequency. Which one has the longest wavelength? radio waves. Which one carries the most energy?
Oh wait, hold on.
Correct answer is D, gamma rays. Energy goes with frequency. Okay. See, science class. That was easy, right?
You can't say that.
This section.
This
The-
questions.
Right. The questions you'll have on the test over electromagnetic waves will be.
Are they gonna be worded like that? Oh wait, that's a different question. Not like that, like the other one.
Okay. So last thing. So I have discovered that you guys, unless you're in honors chemistry, have not done spectral lines, which is like that is like so. Go in the back and grab one of those plastic black boxes or blue boxes.
Oh, yeah, I did this in Owen's chemistry.
Did you?
Yeah.
Nice.
I think I got to see
Yeah.
it last year.
You did it. If you had Chem 2, you've done this as well.
Now what?
Yeah.
On the graph that showed what was let through, why was it so up and down in the infrared section?
Mine's upside down.
I don't know. Some it lets through, some of it doesn't. I don't know. That's a good question.
When I can't see anything.
Okay. Don't worry about it yet. Go ahead and have it. Or stand up. I don't care. All right. So this is hydrogen gas. So what you're going to do to see this is you're going to point the opening. Look at what you're. So you're looking through the narrow end. Look at the wide end. Find the opening. There's only one spot that's an opening, and point that directly at the purple light. Okay. Now, what you're going to do. Oh, hold on. Let me kill the camera. Okay. What you're going to do, depending on which one you're going to do, you're going to put that pink light, shining light through that opening, and then with that still in that position, you're going to look off to the side, right or left, depending on how you're holding your device, and you should see numbers like a scale, and if you look closely enough, you should see stripes of color. Hold the box so it's like a sandwich, like horizontally.
Wait, what are we supposed to do once we find it?
Okay, once you stick the purple light in your viewfinder, look off to the side with your eyeball. Don't move your viewfinder. Keep your viewfinders at that location, but look with your eyeball to your right or left, depending on how you're holding your device. There should be a scale with numbers. Yeah. Okay, look for color stripes.
They're all red.
There should be a green one in there.
Sure. Do you know what number it is? Like.
I don't. Can someone call it out? Turquoise, purple.
This is really hurting my eyes.
Sorry.
I'm not seeing
any. If you can't see it, use somebody else's that does see it.
I can see the numbers, but I can't see the green one.
You have to find it, and you have to way back and look off to the side.
How do you see the green one?
So you have to look way
Oh, I see it now.
Everybody see it?
Oh. I just switched eyes. Oh my god, it hurts my eyeballs.
It's really cool. See, it's a little bit like a.
I see red and green. I don't see what number it is. Actually, I can't see.
Okay.
I can't read the.
This is just proof of concept. I just wanted to have some.
This is a hard to use device.
Okay. Here come the lights. The lights are coming back on. Ready? 3, 2, Okay. Now, that is the color signature of hydrogen gas. Okay. Stars are made primarily of hydrogen. Okay. So the hydrogen gas, I'm making this up. You saw a couple like red lines and maybe a green and a purple, something like that. And there are certain numbers in terms of wavelength, frequency associated with that. So when they looked at stars in distant galaxies through the spectra, like that's technically it's called a diffraction grating. What they would notice is those lines were shifted a little bit to the left side of the spectrum. And they're like, what is up with that? And they're like, that's our device. And so they recalibrated it. They asked other people to do the same thing, and everybody got a consistent reading. Well, maybe it's our atmosphere. They put stuff up in the Hubble telescope, and they observed outside our atmosphere, and same thing. And so the conclusion was stars are demonstrating the Doppler effect. They're moving away from us. And so when you move away, what happens to the frequency? It gets lower. Frequency is shifted to the left to a lower frequency of light. This is known as the red shift. It's moving to the left towards red. And so that was what tipped us off to this idea that the universe is expanding. All the stars in distant galaxies are moving away from us due to the Doppler effect. Crazy. Cool that? I'll lose you on that one.
Wait, is there anything coming towards us?
No. So if everything's expanding, everything, like the analogy is, if you put a dot on a balloon, on a deflated, unblown up balloon, and then you blew it up, or you put another dot anywhere, that dot will always look like it's going away from you. Good with that? And that's the physics show today, kids.